Pure combinational logic evaluates data in real time. It has no memory of the past, meaning its output instantly reflects whatever happens to be on its input wires right now. To build complex architectures like finite state machines or data pipelines, we have to enforce order. We must inject what engineers call state or tokens into the system to physically isolate current calculations from previous ones. Think of a continuous data stream as light pulses traveling down a fiber optic cable. The pulses are launched sequentially, but because of variations in the medium, pulses don't travel at the exact same speed. Soon, faster pulses catch up to slower ones. In digital circuits, this variation is called dispersion. Without physical hardware boundaries to act as checkpoints, fast logic signals will overrun slow ones, blending two distinct computational steps into corrupted data. Attempting to operate a circuit entirely without these checkpoints is a technique known as wave pipelining. Because dispersion in standard silicon is highly unpredictable, relying on wave pipelining carries catastrophic timing risks. The practical solution is to insert rigid hardware barriers. We force the fast signals to wait at a gate until the slow signals finish arriving. This waiting period introduces an inherent delay into the pipeline, known as sequencing overhead. These barriers are a mandatory tax on the system. Engineers intentionally sacrifice a fraction of the processor's maximum theoretical speed to mathematically guarantee that a data collision will never occur. The most primitive form of this hardware checkpoint is the D-latch. A latch is described as a level-sensitive and transparent high device. It operates strictly based on the current voltage level of the clock signal. This diagram details how that sensitivity behaves. When the clock is high, the barrier is open. Any change to input D flows directly to output Q. When the clock drops low, the latch locks the output state. Even as D fluctuates wildly, Q remains static. While it successfully captures the state of the circuit, the D latch leaves the pipeline exposed. For a full half cycle, the barrier remains entirely open, leaving the downstream logic vulnerable to any noise or timing glitches propagating through the wire. Transitioning from theoretical timing to physical layout in deep submicron architectures introduces a stark reality. Managing state is entirely an exercise in managing noise. This is the baseline topology for a tri-state feedback latch. Its flaw lies exactly here, at node X. Because the internal state node connects directly to the transmission gate, any heavy noise on the D input can bleed backward into the logic. This backdriving corrupts the stored state and ruins the calculation. To prevent this, standard cell libraries rely on the buffered input latch. By placing an inverter at the front of the gate, it physically isolates the internal state node from the noisy input wire, eliminating the backdriving risk entirely. The penalty for this physical robustness is severe. Buffered cells require more transistors, consume more layout area, operate slower, and place a heavy loading tax on the clock distribution network. When raw computational speed is the priority, engineers strip those buffers away, utilizing the minimalist data path latch. By removing the protective input buffer, the latch achieves a significantly smaller footprint and much faster switching speeds. The designers trade noise immunity for raw performance. Looking at the physical footprint of the AMD K5 processor, we can see exactly where this risky, ultra-fast logic is deployed across the high-speed integer data path. Physical layout dictates topology. Engineers must constantly balance the bulletproof reliability of buffered standard cells against the dense, high-speed danger of unbuffered data path logic. The structural solution to this timing problem is the edge-triggered flip-flop, often just called a flop. A flip-flop is built by wiring two back-to-back latches together. The first is the master, the second is the slave. Driven by the same clock, their transmission gates are wired inversely. When the master is transparent, the slave is opaque, and vice versa. Data flows into the master latch while the clock is low, securely trapped inside the cyan block. The exact moment the clock snaps high, the master slams shut and the slave opens, instantly passing the trapped data out to the next stage. By cascading two level-sensitive devices perfectly out of phase, engineers compress the wide, transparent window into a microscopic fraction of time, creating the rigid, instantaneous edge that makes modern synchronous processing possible. These physical hardware delays dictate the absolute limits of the processor. To guarantee a chip won't fail under heavy load, engineers map these boundaries using static timing analysis. Logic delay exerts two opposing forces on the pipeline. Propagation delay represents the maximum time it takes a circuit to resolve a final answer. Contamination delay represents the fastest possible time any signal can ripple through that same logic block. We establish the maximum boundary of the clock cycle using the setup constraint equation. For the circuit to function, the overall period must be greater than the propagation delay, plus the time data leaves the flop, plus the setup time to stabilize the receiver. Conversely, the min delay constraint protects the system from data arriving too fast. The fastest signal traveling through the logic must take longer than the required hold time, otherwise it crashes into the receiving flop before it closes, overwriting previous data. The flip-flop enforces a rigid mathematical box for every pipeline stage. If you violate the setup bound, your data arrives late. If you violate the hold bound, your data is corrupted. A hard clock edge creates an inescapable inefficiency. If a specific logic path is short and finishes its calculation early, the flip-flop remains locked. The processor just sits there, completely wasting the remainder of the clock cycle. To reclaim this wasted silicon time, architects deploy an advanced routing technique known as time borrowing. This text outlines the strict comparison between a rigid flop-based system, where early arrivals waste time, and a fluid latch-based architecture. Because a pure latch relies on a wide, transparent window rather than a hard edge, an unusually slow logic path isn't forced to halt exactly when the clock ticks. The slow calculation is allowed to bleed over the half-cycle boundary. It physically borrows time, continuing its computation while the receiving latch is transparent, eating into the time allotted for the next stage. There is one strict mathematical caveat to this flexibility. While individual loops can trade internal timing deficits back and forth, the entire pipeline sequence must still resolve and balance out within one overall clock cycle. Time borrowing proves that the synchronous clock edge does not have to be an absolute wall. By selectively reverting to simpler latch-based architectures, hardware designers stretch time across boundaries, absorb inherent sequencing delays, and squeeze maximum performance out of the silicon.